everyone, and welcome to a new episode of our speaker series. And joining us today is Dr. Nicolle Zellner, a professor of physics at Albion College. Dr. Zellner, would you like to start your presentation?
I will, indeed. Thank you. All right. Well, I am delighted to be here today talking to bright young minds interested in science and engineering and technology fields in general. I was also a young, bright mind, like a lot of you. I grew up in a small town in Wisconsin called Winneconne. Here is the map of Wisconsin, and you can see how I've highlighted Winneconne. It's basically two parts on the side, either side of the Wolf River. Winneconne is famous for having seceded from the Union back in the 1960s when Winneconne was left off of the state map. So the town seceded from the Union and became its own sovereign state. The mosquito was the state bird, poison ivy was the state plant. So you can see that they kind of made a little bit of fun of it. But it was enough to get the map makers to put Winneconne back on the map, and we continue to celebrate Sovereign State Days every July. After I graduated from Winneconne High School, I went to the University of Wisconsin-Madison, where I majored in astronomy and physics with a minor of sorts in math, as well as their certificate in environmental studies. So this was in the 90s, and the Nelson Institute was just getting a foothold in environmental issues and educating people about how to help save our environment, if you will. And this was really appealing to me, having grown up in a rural town, a rural area with lots of farms and a farming economy around me. But I was interested in the math and the physics and the science, and so I spent 5 years getting my undergraduate degree at Wisconsin, and I worked at the campus telescope, which was called the Pine Bluff Observatory. This was a 36-inch telescope that was dedicated to observing celestial objects in the visible wavelength range using something called a spectropolarimeter. The team at Wisconsin made an identical spectropolarimeter that was tuned to the ultraviolet wavelength range, which of course is only visible above the atmosphere. So working at the campus telescope qualified me to be hired to take part in the STS-67 Astro 2 mission, which launched on the Space Shuttle Endeavour in 1995. This was a 2-week mission dedicated to observations of ultraviolet astronomy using 3 telescopes, including one from Wisconsin called WUPI, the Wisconsin Ultraviolet Photopolarimeter Experiment. I'm told we won Best Acronym contest that year, and it was the motivating factor that propelled me on to graduate school and a degree, a PhD in physics. So after working at the Space Astronomy Lab for 3 years after my undergrad, I went to graduate school at Rensselaer Polytechnic Institute in upstate New York. You heard that right. I took a gap between my undergraduate degree and going to graduate school. So I worked for 3 years. I didn't go straight through. I worked for 3 years in between. And I feel that those 3 years really gave me a chance to develop my maturity and also my sense of self, to really know that I wanted to study science and dedicate my life, which has literally turned into my life, to these fields. So I studied at Rensselaer Polytechnic Institute, and I spent 5 years there on a variety of projects, and I'll talk about them in a little bit, and then got hired at Albion College in 2005. I was hired into a tenure track position in the physics department, and shortly thereafter I was selected to travel to Antarctica as part of the ANSMET team. So ANSMET stands for the Antarctic Search for Meteorites, and it is a federally funded expedition that's been going on since the late 1970s to collect meteorites in Antarctica. Meteorites that come from Mars, they come from the moon, they come from asteroids, they come from objects we don't even know about, and they help unveil really interesting stories about their parent bodies. And I'm happy to answer questions about that a little bit later. So while I've been at Albion College, which is a liberal arts college in South Central Michigan, I've been able to really exercise and explore various interests of mine, including the history of astronomy. Albion College has a very robust student research program, as well as a really great faculty development program. So I've been able to use funding to progress professionally, both in my research areas and in the classroom. In 2008, I went to Florence, Italy, where I actually got to see Galileo's original eyepiece from 1610, the one that he used to observe the 4 moons of Jupiter and basically prove that the geocentric view of our solar system was incorrect, and that we, in fact, were a heliocentric system, as Copernicus proposed in the 1500s, because he saw these moons orbiting around Jupiter, and he said, if they're orbiting around Jupiter and not around the Earth, why should anything orbit around the Earth? So he really made some of those observations that clinched the acceptance of this heliocentric model. I have always been interested in the space program, having participated in that space shuttle mission. So here's a picture of the second to last space shuttle launch in 2010. I have a very dear friend who works at Kennedy Space Center, or worked at Kennedy Space Center, and was able to get some VIP passes pretty close to the launch site. If you ever get a chance to see a launch, no more shuttles anymore, unfortunately, but any other kind of launch, please go do it. They're spectacular. I spent my first sabbatical in Australia. I'd always had a desire to go to Australia ever since I was very young at the time, but I met a high schooler who had a little tattoo of Australia on her foot, and I was like, I want to go to Australia. So finally, as a faculty member, I got to take my first sabbatical in Australia, which I thought was my only trip to Australia ever in my life. So I did practically everything you could do in Australia. I called it my first once-in-a-lifetime trip in Australia because it turns out I've gone about 4 times now, 5 I think. Next year will be number 6. So wonderful opportunities to engage in research, collaborations, and also see a part of the world that I never would have gotten a chance to see before. These are just a couple of my other adventures along the way. I'm happy to talk about all of the places I've been if time permits, but being a scientist and a faculty member really allows for visiting parts of the world that are unaccessible or inaccessible to a lot of people because of conferences and collaborations and scientific knowledge sharing, which is so vital and so important in the field of science and engineering and technology. So what do I do at Albion College? I actually study planets. I study the moon in particular. I'm a member of the physics department. I teach introductory astronomy for non-science majors. I'm department chair. I serve on committees. I've worked at NASA. I do a little bit of everything. But I am in a physics department, which allows me then to draw on my original love and passion for a science that is steeped in mathematical insight and basically helps us understand the formation of our universe and how everything in this world works. So my very particular line of research is trying to understand the lunar impact flux, or how often the moon got hit by comets and asteroids over time and where. The moon is the Earth's closest neighbor, and so we use the moon's impact flux as a proxy for understanding the Earth's impact flux. And that's because the moon doesn't have an atmosphere, it doesn't have water, it doesn't have plate tectonics, it doesn't have those things that Earth has that erases evidence of impacts over time. So the samples that we get from the moon have a record of bombardment on the moon and potentially reflect bombardment in the solar system since the solar system's formation 4.5 billion years ago till about the time that the astronauts picked up those samples in the 1970s. The lunar impact flux has been interpreted in a variety of ways. The original idea was that very early on in solar system history, which is on the left-hand side of this plot, there were a lot of things hitting the moon and hitting the Earth and Mars and Venus and all of the planets in our solar system as our solar system was forming. But then over time, as our solar system stabilized, that impact flux decreased in what we call a monotonic decline. In the 1970s, however, after the Apollo astronauts brought samples back to Earth, investigators hypothesized that there was actually some sort of a cataclysmic spike at around 3.9 billion years ago. And this is because the samples that they looked at all had an impact formation age of around 3.9 billion years. So just a small handful of samples, but this idea really held fast for almost over 50 years, basically, with this notion that it wasn't a monotonic decline in impact flux, but was that rather a period of about 700 million years of no impacts, and then a giant cataclysmic bombardment where most of the debris in our solar system that was left over, most of the large stuff, fell on the moon in about a 200 million year time period, and then there were no impacts after that. Not everybody believed this cataclysmic event. Some people felt that perhaps it was just the final bombardment that erased all of the previous bombardments because it was so big. And by erased, I mean craters were formed from bombardment that covered up the older craters. So trying to understand this bombardment scenario is important, whether it's a monotonic decline, a cataclysm, a sawtooth, an intense bombardment, because around this time period, in the first 700 or 800 million years of Earth's history, we're starting to see some really interesting biological and geological events happening. For example, at about 4.3 billion years ago, so 200 million years, 100 million years after the Earth formed, we started to see evidence for liquid water on the Earth, so cool liquid water. We also start to see evidence for some kind of land mass. 500 million years later, at around 3.8 billion years ago, we start to see evidence for the first life, not fossils, but rather carbon isotopes. Isotopes of carbon that are only used by life have been preserved in some sedimentary rock in some of our oldest areas on the Earth. And then by 3.5 billion years ago, so about a billion years after Earth formed, we start to see the first fossil evidence for life on Earth. So if we understand what this bombardment scenario looks like, we can start to put into a larger context some of this geological and biological evidence that we see. That's not the only hypothesis about bombardment, however. Recent studies have also hypothesized that there's been an increase in the last 500 million years or so of Earth's history. So this is where my interest lies in trying to understand this bombardment history and how it relates to interesting biological and geological events on Earth. And if we're clever enough, how we can extrapolate the moon's bombardment history to Mars, right? And potentially Venus and Mercury as well. So I study a very particular kind of impact sample called a lunar impact glass. Just like glass is formed here on Earth by melting sand, the impact glasses on the moon are formed when an asteroid or a comet smacks onto the surface of the moon, and then in that heat, that high temperature, high pressure impact event, the regolith, which is the lunar dirt, gets melted into these droplets of impact glass. You can't see them with your naked eye, usually, because they are very small, usually about 250 microns or smaller, though there have been some impact glasses that have been about 0.5 millimeter to 1 millimeter in size, and certainly you can see those with your naked eye. The regolith itself looks like a brown talcum powder, but of course it's very coarse rock that's been bombarded and beaten up over billions of years. But underneath a microscope, you can start to see these beautiful little gems of glass. So these little gems of glass get hand-picked out of the regolith. They get placed into analytical mounts that then go into an electron microprobe where the composition of the glass is determined. When we look at the moon, we see large dark areas, which are called the mare or the seas. And these mare are the lava-filled impact basins that contain a lot of iron and titanium. We also see brighter, lighter areas that we call the lunar highlands. And these don't have a lot of iron and titanium, but rather have aluminum and calcium. So that's what gives it their lighter color. So by finding out the chemical composition of these glasses, we can get a sense as to whether or not they were formed in a mare area, like this dark orange shard here on the screen, or if they were formed in a highland area, like this green, bluish tinted spheral on the screen. So a ternary diagram, which is that triangle that you see in the middle, kind of gives us a sense of where these glasses formed in compositional space. After we have the composition of the glass and can start to assign some sort of a regional provenance to them, then we blast them with a laser in order to extract the argon. So the glass actually forms with potassium in it, because we find potassium in the regolith. The potassium decays into argon, and then we blast the samples with neutrons so that we can force an isotope of potassium into an isotope of argon. We extract the argon isotopes out with an argon mass spectrometer, and we get something called a formation age, or when all of the step heating of that glass forms this really nice plateau. So here we see an Apollo 16 sample, number 185, with an age of about 3.7 billion years, plus or minus 0.009 billion years. So very old age with a very small uncertainty. And you can see that that's a really nice plateau. All of those steps are telling us the same age. So you do this enough times, and you start to put them together in a histogram of sorts. So this is called an ideogram. It's basically a Gaussian distribution of sample ages. We've got the oldest ages on the left-hand side. We've got the younger ages on the right-hand side. And you can start to see that there are some really interesting trends that these glasses are revealing. And so I've published on this a number of times, and I continue to do work to try to add to the data set. As a data scientist, I feel like more data, more better, to really reduce the error, reduce the uncertainty, and increase the signal over the noise. We see this dearth of impacts between about 1,800 million years, 1.8 billion years, and about 3.2 billion years. In there, we start to see potentially spikes in the impact record early on in that in the more recent billion years, and we see this influx of impact activity in the older part of our solar system. So these are the things that these are the trends that I try to decipher. My other experiment is actually doing impacts in the lab. I work with a chemistry professor at Albion College. That's the beauty of working at a small liberal arts college. I'm really able to interact with other people on campus in other disciplines. And we're taking a very simple sugar called glycolaldehyde. And it's a 2-carbon sugar that's been found ubiquitously in space. It's been found in star-forming regions. It's been found on comets. It's been found in the clays on Mars. It's been found on Europa. And we're subjecting it to simulated impact at the Experimental Impact Lab at Johnson Space Center. We smack a capsule that's filled with glycolaldehyde, and then we extract the impacted material and analyze it with a gas chromatograph, a GCMS, gas chromatography mass spectrometer. Again, it gives us a mass of the sample, and then with that mass, we know what it is that we're looking at. And it turns out, and we published this in 2020, we published the analytical technique in 2014 with 2 student co-authors, and we published some calculations in 2022 with a student co-worker. It turns out that almost all of the glycolaldehyde survives impact or changes into really interesting biomolecules necessary for life as we know it. And it's important that the glycolaldehyde doesn't survives intact. It's important that the glycolaldehyde survives intact because glycolaldehyde is a starting ingredient for the foremost reaction, which creates ribose, as in RNA, ribonucleic acid, right? The ribose, the sugar backbone of our DNA. And it's a vital starting ingredient for structure synthesis, which creates amino acids. So we've shown that delivery of glycolaldehyde by comets, in particular, is a really good source for these really important chemical reactions that are important for the origin of life on Earth and life as we know it then, potentially in our solar system. Here are just a couple of my student projects that I've done with students over the years. Albion College is an undergraduate-only institution. Physics in particular has a very keen interest in helping our students learn about physics and applying physics to other topics, whether it's telescope building or astrophotography or astrophotography over here as well, or sample analysis. We also do a lot of public observing sessions to get the students experienced in using the telescopes and the public excited about looking at space and space topics in general. My current projects include analyzing Apollo 15 glasses, and I'm doing some data analysis on it. I've got 2 students working with me on a NASA grant to do that. We're continuing to conduct impact experiments. There's a really interesting crater on the far side of the moon called Molten Crater that is named after an Albion alum from the class of 1894. He was very famous in the early part of the 20th century in terms of understanding and proving different theorems related to celestial mechanics. So I've got some students working on the geology of Molten Crater using the high resolution orbital data we have of the far side of the moon. We are actually a collection hub for solar eclipse glasses. We've gotten over 10,000 glasses sent to us. So we're sorting through them right now, and we're saving them for distribution to lower income countries around the world as part of the Astronomers Without Borders project. So we're really happy to be able to save those objects from a landfill and have other people use them who wouldn't otherwise be able to afford them. We have a brand new retrofitted Celestron 14-inch telescope that is capable of taking high-resolution images and data of variable stars and asteroid tracking. So we've got some students getting trained up on how to use that. And then finally, as I said, I got really interested in history of astronomy, and in particular, the First Lady astronaut trainees, a group of 13 women who were recruited to undergo the same tests as the NASA Mercury 7, but were denied travel to space because that's just not what women did at the time. So I've done some research and some writing about those women as well. So that's a little bit about me and what I do. And with that, I'm happy to answer any questions that you have. Thank you.
Okay, yeah,
so
Nicolle, you.
Okay, thank you. So Dr. Zellner, thank you so much for coming and presenting for us again today. The first question that we have for you is, what do you enjoy most about your job, and what would you say keeps you passionate about planetary sciences?
Okay, 2 different questions. What I love most about my job is the students. One of my visions early on in my career was that I wanted to teach. I feel that educating our country, our students, kids your age, younger and older, about the importance of STEM, especially mathematics, is essential if we are going to be a leading country in science and technology development. So I love teaching our students about science, and in particular, I love teaching the non-science majors. I feel like the science majors are already a captive audience. They've already got that desire, that passion, that fortitude and persistence, I guess is the good way to say it. And they've already chosen to go into science. But the non-science majors, right, the ones who hate math or can't do math or whatever other excuse I get, these are the ones who are going to be our policymakers, they're going to be our lawyers, they're going to be our congresspeople, they're going to be our doctors, right? They're going to be a whole plethora of jobs that usually scientists are not. So having them appreciate the value of science, and if they even can't do math, at least appreciate what a useful tool it is, I think is really of utmost importance. And so that's what I love most about my job, is interacting with the students and really helping them appreciate and value science. What do I like most about the field of planetary science? I think it's that we're still learning stuff, right? We are still learning new things from the Apollo samples, even though they were collected over 50 years ago. We are still learning new things about the Apollo samples. I mean, that's just mind-blowing, right? NASA back in the 1970s was very clever. They preserved some of the sample in vacuum to be opened at a later date when technology, when instruments got to be more advanced, and that is happening now. We're opening these samples now 50 years later, and we're learning so much about them that's helping us learn more about the moon. We're sending missions to Europa that's going to launch later this year. We're sent the Europa Clipper. We sent a mission to a metal asteroid, an iron nickel asteroid. Psyche had a launch last year, right? We're going back to the moon with Artemis. We're sending Dragonfly out to Titan. We've got a whole cadre of a whole fleet of spacecraft and rovers on Mars, right? So it's a very, very exciting time to be learning about planetary science, about the solar system.
Yeah, wow, that's very interesting. I think you mentioned how things are always changing and how you're always learning new things, and how in general how quickly the field is moving. So how have advances in technology impacted, the future of this field as well as your own research?
Yeah, that's a really good question. So I look at really small samples, and 50 years ago it was not possible to look at small samples, and so they actually looked at what we call bulk samples. They just put a bunch of stuff together and did a bulk analysis. And what we've learned over 50 years is that really introduces a lot of noise. So this 3.9 billion year cataclysm signal I shared with you turned out to be Imbrium ejecta that we were analyzing over and over and over again, because Imbrium, being the largest basin on the near side of the moon, its ejecta, its material from impact, had embedded itself into almost every other kind of sample that the Apollo astronauts collected. So this 3.9 event that we thought was happening all over the moon was actually just one event that we were dating over and over again. Now, more than 50 years later, we can take individual tiny samples, microns in size, nanometers in size. We can analyze that little tiny sample, and we can extract the information from it as well. So the ability to look at smaller samples, analyze smaller samples, that's really been a huge advancement in terms of sample science.
Wow, yeah, that's great. So you had mentioned your participation in ANSMET. So what is a typical day like for a scientist there?
Well, a typical day is every day's the same. So when I was there, 2006, 2007, we would basically get up and put on our cold weather gear, fuel up with something cooked in butter, and a hot chocolate or a coffee or something like that, and we would leave for the day on our snowmobiles. So meteorites are really easy to find in the blue ice fields of Antarctica, where the katabatic winds are coming off of the Antarctic plain and kind of blowing away the snow and ablating the ice. So the ice has been laid down for tens of thousands of years. The meteorites fall into that ice. And then as that ice is getting ablated, right, like ice cubes get smaller in your freezer, as the ice is getting ablated, the meteorites appear, right? So we go out to these blue ice fields, and then we very systematically search the blue ice field. Every time we find a meteorite, we stop. We go to the meteorite, we collect it with sterilized tongs, we put it in a Teflon bag, we label it, we mark its GPS location, and then we get back on our snowmobiles and we do this. We do this all day. And we break for lunch, and then we'll work for another 3 or 4 hours. And then we go back to camp, fuel up the snowmobiles, get them ready for the next day, unpack, unload the meteorites, put them into the cold storage area, and then have our nighttime activities, dinner, social hours, phone calls, however. Now, we're there during the austral summer, so it's daylight all day long, and you just see rather than the sun rising and setting, right? You see the sun moving along the horizon. It's wild. But yeah, that's a typical day. If it's very cold, then we'll come back early, right? Because you don't want frostbite, you don't want to lose circulation, you don't want to, if you're not thinking correctly, right, you could do something really stupid. So we always have a safety officer at each of the camps, and it's their job to make sure that we're doing okay as people, and also that our equipment and everything is keeping us safe. And you do that for 6 weeks, every day for 6 weeks, unless it's a snow day, or a tent day, where it's either snowing or there's too many clouds and it's overcast and you really can't see shadows or anything like that. So yeah, that's what we did.
Wow, yeah, that sounds really interesting. Our last question for you today is, how can high schoolers that are interested in planetary sciences get further integrated into that career path?
Super good question. So I think, number one, do a Google search. Search the internet, find out what colleges, universities are doing planetary science. As high schoolers, NASA actually has high school internship positions available. So if you go to intern.nasa.gov, you'll see options for high school students to do internships. NASA Ames, where you all are located very close to, I believe they also have some high school opportunities, as well as JPL, the Jet Propulsion Laboratory in California. There are lots of other schools around the country who also do research in planetary science. I think that, my degree is in physics, right? I'm a physicist. That's how I identify. I am not a geologist. A lot of people in planetary science are geologists, but they're also astronomers, they're also computer scientists, they're also data analysts, they're physicists. So there's an angle into planetary science from pretty much any direction, and especially science writers, right? We need really good, qualified science writers, people who can write about science in an intelligent way, to make it accessible to the general public. So lots of opportunities, lots of ways in, but certainly it's a STEM degree, and it requires a STEM degree, but again, lots of roadways, lots of avenues into the field in general.
Okay, thank you so much, Dr. Zellner. So that's going to conclude our interview for today. Thank you so much for answering those questions with really profound answers. That was really nice. And take care, everyone. We'll see you all next time. Bye-bye.